So in this video, we're going to look at a simple case where we find the area between two curves when we have vertical representative rectangles and when we're given the interval over which we want to find the area. So first thing to recognize is that the representative rectangles just as simple, it's simply a matter of you looking at the interval over which you're integrating. So we want to find the area between the curves f of x and g of x over the interval from 1 to 2, and drawing in one rectangle that represents a rectangle area that's being found as you integrate to get the area between the two curves. And on that representative rectangle, what you want to recognize is that the width of it is a delta x, but because we're going to be integrating, we'll represent that with a dx. So this tells us that we're integrating with respect to the x-axis. The second thing is, in video 1, when we developed the concept of finding the area between curves, we came up with a slide that had this nice little formula on it, that the area is just the integral from a to b of f of x minus g of x dx. What we need to remember, though, is that this formula was predicated on f of x being the function above and g of x being the function below. So g of x has to be less than or equal to f of x in order to use this formula. So when I look here at the two functions I'm being given, this example is here explicitly because f of x is not the function above. F of x is a parabola opening upwards. So f of x is actually the lower parabola, and g of x, we can see because of the negative sign on the x squared term that it's a parabola opening downwards. So the upper function is actually g of x. So we don't want to just blindly plug functions into a formula. We need to understand the spirit of the formula, which is take the function that's above, which in our case is g of x, and subtract from it the function which is below, which in our case is f of x, to get the distance between the two, the positive distance between the two functions. So once I identify that, I can go ahead and set up my integral. We're looking to find the area between the two curves, between 1 and 2. So we're going to integrate from 1 to 2. And in this case, it's going to be g of x, which is negative x squared plus 2x plus 3 minus f of x, because f of x is the function below. And I need a parenthesis so that that minus will distribute into the parentheses. And then I close off my full parentheses so that I'm not violating the distributive law, and I have my dx. And then I can do a little simplifying inside the parentheses. This is the integral from 1 to 2 of minus x squared plus 2x plus 3 minus x squared minus plus 4x minus plus minus 3 dx. And then collecting like terms, we'll get minus x squared is minus 2x squared, plus 2x plus 4x is plus 6x, and 3 minus 3 is 0. So we wind up with minus 2x squared plus 6x dx. Now integrate, some parentheses. Integrating, we're going to get an x cubed, and we'll need a negative 2/3 to kill that 3 when we differentiate. And then we're going to get plus, and it's going to be x squared. The exponent goes one larger, and I need a 3 here. So 2 times 3 to give me my 6 if I differentiate. And we integrated from 1 to 2. Now we just plug in our bounds of integration. So we have negative 2/3 x cubed, but x is getting replaced with the 2, plus 3 times 2 squared, minus parentheses, plug the 1 in. But plugging in a 1 is just going to give us a negative 2/3 plus 3. And now we just need to distribute and simplify. So this term here looks like a negative 16/3. Plus this looks like a 12. A double negation is a plus 2/3. And a minus 3. So we get a negative 16 plus 2 is a negative 14/3. Plus 12 minus 3 is a 9. And then, of course, we need common denominators. So it's going to be negative 14. And 9 times 3 is going to be plus 27, and it will be over the common denominator of 3. And so we're going to get, it looks like 13 thirds as the area between the two curves.